Okay, basics of probability. Basic definitions. A sample space is a set, usually called S. Outcomes of some experiment. An event is a subset of the sample space, usually called E. If all the outcomes are equally likely, then the probability is the number of the outcomes that you like, right, the cardinality of E, divided by the total number of outcomes, which is C, which is the number of things in S. So if we roll a six-sided die once, what's the sample space? Well, what happens when you roll a six-sided die once? You get one of these six numbers. And we're assuming these are all equally likely. We're assuming that we don't have a die that has been weighted in some weird way. So the probability of each outcome is 1 out of 6. So probability of 1, this is notation. Oh, usually I don't have the R. P of 1, this is the probability of rolling a 1. Right? So an event is a subset. Rolling an even number is the subset 2, 4, 6. Those are the even numbers that are included in my outcomes. So the probability of rolling an even number is 1/2, right? Because there's 3 things here out of 6. And all the outcomes are equally likely, so the probability of getting an even number is 1/2. So that's a basic idea of probability here. Figure out the number of possible outcomes, figure out the number of outcomes that you like, look at the fraction. So one of the problems is figuring out what is the possible outcomes. So 2 six-sided dice are rolled and the numbers on the top are added up. What's the probability of rolling a 7, of rolling a 10, or 1 over 2, rolling a number greater than 2, of rolling 0, bigger than 0 but less than 13? So first thing is, what's the correct sample space? This one or this one? This is the outcomes you get by adding them up, but these are not equally likely. If you ever played D&D or anything like that, you know that getting like a 7 or 8 is much more likely than getting a 2 or a 12, right? So not equally likely, so that's not our sample space. This is our sample space, right? There's 36 possible outcomes. You get a 1 on the first die, 1 on the second die, 1 on the first die, 2 on the second die. 1 and then 2 is different from 2 and then 1, right? Because this is 1 on the first, 2 on the second. This is 2 on the first, 1 on the second. Different orders, but they add up to the same thing, right? So our number 3 here is actually a result of 2 separate things, but the number 2 is a result of just 1 possibility. So these are not equally likely. These all are. So what's the probability of rolling a 7? Well, it's going to be something over 36. Which of these outcomes add up to 7? It's actually these 6 outcomes along the major diagonal. Those all give you 7. So 6 out of 36. Rolling a 10, these 3 outcomes give you a 10. So 3 out of 36. Twice as likely to roll a 7 as you are a 10, as it turns out. A 1 or a 2. So probability of a 1 or a 2. There's only 3 ways to, it should be a 2 or a 3, I think. 2 or 3, there's no way to get a 1. So that would also be 3 out of 36. So you're just as likely to get a 10 as you are to get a 2 or a 3. Rolling a number greater than 2. Well, the only way to get a 2 is this. Right? So that's a complement. 100% chance of getting some number between to get one of these outcomes. There's only 1 in 36 chance of getting a number that's not 2. So the probability of getting a number that's more than 2 is a 35 out of 36. There's 1 out of 36 ways to get a number that is exactly 2. So 35 out of 36 is the way to get a number that's more than 2. Probability of rolling is 0. 0. There's no outcomes that add up to 0. This is called impossible, right? If the probability of something is impossible, is 0, then it's impossible. Probability that you roll some number that's bigger than 0 but less than 13. Well, all of my outcomes are that. Right? That's called certain. Right? Probability is 100%. Notice that when we're doing probabilities, we think of them in terms of fractions rather than as percents usually. But you can go back and forth. So impossible means probability is 0. Certain means probability is 1. Okay, so if we're dealing with weighted dies, suppose you have a die so that 1 happens a third of the time, 2, 3, and 4 each happen a ninth of the time, 5 and 6 happen a sixth of the time. So probability of 1 is 1 out of 3. Probability of 2 is 1 out of 9. Probability of 3 is 1 out of 9. Probability of 4 is 1 out of 9. Probability of 5 is 1 out of 6. Probability of 6 is 1 out of 6. So it's a weighted die of some sort. Notice that if you add these all up, this adds to is 1, right? You're going to get 1, 2, 3, 4, 5, or 6. You're just not going to get them in the same orders as we thought we had before. So this is what's called a probability distribution. This is my probability distribution. Each event has a particular probability, and the sum of the probabilities is 1. What's the probability of rolling an even number now? Well, it's the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6, which is 2 ninths plus 1 sixth. I suppose that would come into 18ths for, what's that, 7 out of 18, whatever that is, a little less than 50%. So probability distribution, every event gets a probability, but they don't have to be equally weighted. You just have to make sure that the sum of your probabilities adds up to 1. And then you can calculate the same sort of things. Sometimes when you are dealing with percentages, when you're dealing with probabilities, often given in terms of percentages, sometimes in dealing with probability questions, it's a little bit easier for me to imagine that I have, say, 1,000 cases and then figure out the numbers from the percentages rather than dealing with the numbers themselves. So suppose we have this example. 10% of college students have purple socks, 15% of college students have green hats, 40% of students with purple socks have green hats. What percentage of students with green hats have purple socks? Okay, so here's a table. I'm going to assume that I have 100 students. Right, so if I have 100 students total, how many of them have green hats? Well, 15% of 100 is 15. How many of them have purple socks? 10% of college students have purple socks. So that means out of my 100 students, 90 do not have purple socks and 85 do not have green hats. Great. And they give us this, 40% of students with purple socks have green hats. How many students have purple socks? 10. So So 10 students have purple socks. 40% of those have green hats. That means I have 4 students that have purple hats and green socks. So 11 have green socks but not purple hats. 6 have purple socks but not green hats. And most everybody, 79, have neither. So you can set up the same thing, same table, right, by just putting in the percentages. That's just dividing everything by 100. So this 4 then the percentage, take the percentage of students that have purple socks and then multiply that by the percentage of people with purple socks that have green hats, and that's 0.4, so that gives me my 0.04. And then 0.11, 0.06, 0.79, it's table here is just everything up there divided by 100. It's easier for me sometimes to think about these things in terms of 100 students instead of in terms of percentages. So that's why I do that. So percentages of green hats with purple socks. So how many people have green hats? 15. So out of those 15, how many have purple socks? 4. So 4 out of 15. But notice that when we're doing this, we're not looking at all 100 students. We're just looking at the people with green hats. There's 15 of those. How many of those have purple socks? So it's 4 to 15. Okay. So combination lock is 3 digits. These really should be called permutation locks. It's probably guessing the correct combination. Well, there's 1,000 possibilities, right? You've got 10 choices for the first digit, 10 choices for the second, 10 choices for the third. Your combination might be 1, 2, 1, might be 7, 3, 5. There might be repeats, there might not. So there's 1,000 combinations. How many are the correct combinations? 1 out of 1,000. Get the correct combination. Okay. Now, a standard way to think about some of these, a standard object for thinking about probability is decks of cards. And we like decks of cards mostly because they can be divided up into lots and lots of different subsets. So here's a deck of cards. There's 52 cards total. Aces, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jacks, queens, kings. So 4 of each type. 26 red cards, hearts and diamonds, 13s of each. 26 black cards, spades, and clubs. And so when you're doing teaching probability, you use cards a lot because they can be just chopped up in so many different ways. So if I pick 5 cards at random from a standard deck, how many possible outcomes are there? How many different drawings of 5 cards are there? Well, I want 5 cards. I'm not worried about what order I get them in. So C52, 5. Right? Choose 5 out of 52. If you're ever choosing more than one thing, it has to be a combination or permutation. And not in order, so it's a combination. So that's how many different possibilities are. So what's the probability? Exactly 2 face cards. If I draw 5 cards in total. Well, what I need is 2 face cards, and then I have to choose 3 not face cards. Because I'm thinking about 5 cards total, right? If exactly 2 are face cards, and the other 3 have to be not face cards. How many ways are there to pick that? Well, there are 12, right, deck of cards. There's 12 face cards, and there's 40 non-face cards. So I have to pick 2 face cards out of the 12 possible ones, and then I have to pick out of 40, 3 non-face cards. So that's how many ways there are to pick 2 face cards and 3 non-face cards. So the probability that I pick exactly this grouping is this many outcomes divided by the total number of outcomes. So C52.5 on the bottom. Okay. So what's the probability of getting exactly 2 face cards and 2 10s? Well, I would have to pick 2 face cards out of the 12 that are possible. And then I have to pick 2 10s out of the 4 possible 10s. And then I have to pick 1 more card because we're picking 5 cards and I've only got 4. So 1 more card. How many cards are left? Well, there's 52 cards total, 12 face cards, that takes me down to 40, minus 4 more 10s, that takes me down to 36. So a card that's not a face card, not a 10. So that's the number of ways to get 2 face cards, 2 10s, and some other card, divided by the total number of outcomes to get the probability of getting exactly 2 face cards and 2 10s, also called 2 pair. So one of the things that's interesting with cards, if you ever play poker or anything, is what's the probability of getting things like a full house or a flush or a straight flush or anything like that. So suppose we think of getting 5 cards drawn from a standard deck. What's the probability of drawing a full house? So that's 3 cards of one rank, 2 cards of another. So say 3 threes and 2 queens, right? That would be a full house because I got 3 out of this column and 2 out of that column. So often when we're trying to figure out probabilities for poker or something, build a hand as a sequence of choices. Right? So each of these columns is called a rank. Right? There's ranks of threes, ranks of queens. So you choose one rank. And then choose, well, it's indented here, and then choose 3 of the 4 cards of that rank, and then choose another rank, and then choose 2 of those 4 cards. Right? So it's a sequence of steps. First you choose a rank, then you choose 3 out of 4 of those cards, then you choose another rank, then you choose 2 out of 4. So 13 ranks to choose from. Picking 3 things out of 4 is 3 out of 4. Choose another rank. Well, there's 13 ranks, but we already choose 1, so there's 12 left, and then pick 2 of those. And since it's a sequence of steps, you multiply them all together. Divide by the total number of outcomes. And so that's probability building a full house. And if you want to figure out what the probabilities are in poker, you can grind through several examples like that.